All right, so what we're going to talk about is what happens when the nucleus starts to break down. Okay, so that's sort of like decomposition, if you will. And that decomposition, we actually use the word decay. So the decay means it's starting to break down. Now, there are lots of different kinds of decay. We only need to know about 3 kinds of decay in this class. All right? One is what you saw in the lab yesterday, and that's when we get alpha particles, okay, coming out. So if an alpha particle leaves the nucleus, that's alpha decay. Okay, if a beta particle leaves the nucleus, that's beta decay. If a gamma photon leaves the nucleus, well, technically it is a form of decay, although we often don't call it that because it's kind of hard, at least in the high school level, to understand why it is that gamma is both energy and a particle at the same time. Okay? So gamma radiation is a form of light. Now, one of the things I sent you guys, I sent you an email with a link to a video reminding you about the electromagnetic spectrum. Okay, it's something you should already know, but if it's kind of fuzzy or you don't remember it, take a minute or 2 or 3 or 5 minutes, whatever that long that video is, and look at it. Okay, because you need to know generally about the electromagnetic spectrum. Okay, so what we see looking at this video or this display on the screen here, we're seeing electromagnetic radiation. But that electromagnetic radiation is coming at us in the form of kind of packets of waves. All right, electromagnetic radiation is in the form of waves, but these waves that we see are coming at us in little packets of these waves, and we call those photons. Okay, if you're a fan of Star Trek, okay, if you're a Star Trek geek like me, you've heard of photon torpedoes. Well, they're I don't know what that is, but they got a bunch of photons, okay? They're firing at you. The reason that lasers work has to do with the fact that those lasers are made of packets of wavelength. Okay, those photons are coming at you. All right? So electromagnetic radiation behaves like waves, but it also behaves like particles, which is kind of cool. You know, it's the duality. Sometimes they call them wavicles. You know, it's kind of neat. They have to come up with names that don't seem to make any sense because the behavior doesn't make any sense if you try to put it in terms that we all understand, things we can touch and see. All right. So if we were just talking about the nucleus itself sort of starting to break down, that's decay. Now that decay means that these alpha, beta particles and these gamma photons are actually coming out of some part of the nucleus. And decay then, when those leave the nucleus, we call that emission. All right? And the combined effect of a lot of emission is what we call radiation. Okay? So decay is what the nucleus is doing. Emission is when these particles or this electromagnetic radiation photons, these packets of electromagnetic waves, when they leave an atom, it's called emission. And then the combined effect of all the emission is called radiation. Does that make sense? All right. Now, alpha can be used to describe the radiation, or we can use it to describe the particles. Okay? If we have a lot of particles coming out, it's alpha radiation. Okay? If we want to talk about an individual particle, we want to talk about its structure, what it's made of. So alpha particles are made of 2 protons and 2 neutrons. 2 protons and 2 neutrons. All right. Those of you who remember a little bit about the structure of the atom from physical science, do you recall anything else that's made of 2 protons and 2 neutrons? What? The helium nucleus. So an alpha particle is, in a practical sense, has the same structure as a helium nucleus. But it's not a helium. Helium has also 2 electrons in addition to these 2 protons and 2 neutrons. Okay? And it doesn't come out of the nucleus. An alpha particle does. Now, could an alpha particle eventually become a helium atom? Yeah, probably so. If it gets out into, the greater world around the atom and, collects 2 electrons, then you got a helium. Sure, that could happen. But when it's coming out of the nucleus, it doesn't have any electrons, and we call it an alpha particle if it's made of 2 protons and 2 neutrons. So if I have an atom that goes through alpha decay, it's going to lose 2 atomic numbers because it's losing 2 protons. Okay? It's also going to lose a mass of 4 because each of these protons and neutrons have 1 AMU mass. Okay, 1 atomic mass unit. A proton and a neutron weigh 1 atomic mass unit. Okay? Got that? The reason that most hydrogens have an atomic mass of 1 is because they only have 1 proton. Okay? All right. Now the symbol for alpha is the Greek letter, like our letter A. Okay? Looks like that. Kind of looks like that. It's like the small letter A with a little switch across the top. Does that make sense? That's the symbol. Excuse me. Now, in order to make the math that we do when balancing nuclear equations a little easier, we're going to put some extra symbols around this alpha particle. Now, if I just want to write and talk about alpha radiation, I'll just use this symbol. That's it. But if I want to do the math that I need to do to balance a nuclear equation, then it's easier for me and easier for you, and that's why I'm going to require you to do this, is that you always put the mass number in the upper left and the atomic number in the lower left. So right up here, kind of like an exponent but on the opposite side, we're going to put a mass number. If it's 2 protons and 2 neutrons, that's a mass number of 4. Okay? And the atomic number is going to go down here, and what's the atomic number of something with 2 protons? 2. Okay? All elements are numbered by the number of protons. Okay? So this is going to have the same atomic number as a helium atom. But it's not a helium atom because it doesn't have the right structure. It doesn't come from the right place, the same place. All right, you with me so far? Yep. All right. Beta. Beta is essentially an electron. But we don't call it an electron because it doesn't exist where electrons exist, or at least initially. It comes out of the nucleus. Okay? So it leaves the nucleus. An electron leaves the nucleus. We call it a beta particle instead of an electron. But the electron, the part of the nucleus it comes from a neutron. Okay? So it's coming out of the nucleus, but it's coming out of a specific part of the nucleus. Coming out of the neutron in the nucleus, or one of the neutrons in the nucleus. Okay? Well, what that does is it changes the neutron into something else. So, inside the neutron, there are lots of particles. Those particles have a bunch of names we don't get into in high school chemistry, but the neutron has positive particles in there and negative particles in there. And for that matter, protons do too. They just happen to have one more positive particle than negative particle. That's what makes it positive. If we pull out this negative particle, an electron is negative. We pull a negative particle out of a neutron. What we leave behind is a positive particle. We'll have one more positive particle inside that subatomic particle, making it a positive particle. Well, because an electron and And a beta particle has so little mass. We talked about this a minute ago. It's like 1,850th the mass of a neutron or proton. Taking an electron or a beta particle out of a neutron doesn't change its mass significantly. We can say its mass is still going to be 1 AMU. So if something has a mass of 1 AMU, but it has a positive charge, what is it? What? A proton. So when you take an electron out of a neutron, or really a beta particle out of a neutron, we're creating an extra proton. We're getting rid of a neutron, we're creating a proton. Okay? So, one less neutron, one more proton when you have beta emission. That make sense? Alright. Gamma radiation. Gamma radiation is the most dangerous high energy type of photon. And it has a certain amount of mass, but its mass is way smaller than even an electron. So it's not going to change the mass of the nucleus at all. Or I didn't give you the atomic symbols for this. Beta is, let's put it over here. Looks like this. It's kind of a B with a tail on it. Capital B with a tail, sort of like a capital B with a tail on it. Okay. Since its mass is so small, we can ignore it. We're going to call its mass 0. Because of the way that we do the math in nuclear equations, we're going to show its atomic number in a kind of a strange way. Okay, because it's creating a proton, and because proton numbers go at the bottom on the left, the way the math works out, this becomes a -1. I'll show you that in a little bit. Okay? Now there's technically no such thing as a negative proton. All right? That doesn't make sense, but the math works out if we do it that way. All right, now gamma. Gamma is electromagnetic radiation. But it's really, really, really short wavelengths. If you have electromagnetic radiation with really, really, really long wavelengths, like 2 or 3 times the length of a football field, you got radio waves. So every time you turn your radio on your car, those are really long electromagnetic waves that are causing that. Okay? And then you get shorter wavelengths and you get microwaves. And shorter wavelengths than that and you get infrared, which is, we feel heat from infrared. Okay? It's also, if you have night vision goggles, you're looking at infrared radiation. And then you got this tiny little slice we can see called visible light. And that's shorter than infrared, right? And so you get shorter than that, the part we can't see, you get ultraviolet. And that's the stuff that causes sunburns. It's also the stuff that can cause cancer if you get too much of it. And it can break apart chemical bonds and things. And then shorter than that, and you get X-rays. And we know what you do with X-rays, right? Yeah, I mean, you've had X-rays at the dentist. And what does the X-ray technician do when they give you an X-ray?
Put on a little metal
They put the apron on you, right? And what do? They leave the room. That's because if you get too many X-rays, that can cause cancer. Okay? And they try to keep you from having too much exposure to X-rays by putting that lead apron on your torso, right? Now, of course, if you have to have an X-ray of your lung, they don't do that. But you know, it's especially important for women because then you can have birth defects if you have too much exposure to X-rays and things. Yep.
Is the apron like absorbed the rays?
Yeah. Yeah, it's filled with lead, and the lead. Well, without going too far down that road, the electrons in the lead absorb those photons of X-rays. they re-emit those X-rays, but they also can re-emit them as longer wavelengths that are less dangerous. And because lead is so dense, it's pretty good at protecting things. But what the X-ray technician does is stand outside a concrete wall, which is also a really good way to shield yourself from X-rays, but we can't put a concrete wall on your torso. Okay? I didn't get a chuckle out of that. I thought that was funny. All right. Anyway. And so gamma radiation we just don't mess around with. Now there's gamma radiation in this room right now. Okay, there was gamma radiation coming out of the uranium ore we were using yesterday. But your body's designed to handle a certain amount of radiation. Okay, you can't get away from radiation. I mean, even if you go down in the earth a mile in a cave or something, there's still radiation coming out of the rocks. The reason we have a mixture of solid, liquid below the surface of the earth, and we have the way our planet works, is because there's so much radiation down there. It keeps the center of our earth hot, okay, which allows us to have this core that spins, which creates a magnetic field around the earth and protects us from all that radiation from the sun. So we need radiation, we just don't need too much of it's a bad thing, okay? So the amount of radiation you were exposed to during the lab yesterday is so small, it's less than you would be exposed to on a daily basis in this building. Okay? You're going to get more radiation from the building itself on a daily basis than we had in that lab yesterday. So it's not dangerous. Okay? So it's a form of electromagnetic radiation, but its mass is so small we can ignore it. So it has a zero mass. It doesn't do anything to the protons. So that's zero. And the symbol is like an L, a script L, that we spin 180 degrees. Okay? Got that? Make sense? All right. But writing these symbols this way, it's going to make our nuclear equation stuff a little bit easier to do. Now, there's one other nuclear particle we need to work on, understand, to be able to do nuclear equations, at least the type that we do in this class. All right, and has nothing to do with decomposition of the nucleus. Well, it kind of does. We'll talk about it. And while we're here, though, we're going to kind of talk about this thing called this neutron. Okay, and a neutron we're going to simply symbolize as a small letter N. And what's the mass of a neutron? 1 atomic mass unit. And so that goes at the upper left. Okay? And how many protons does a neutron have? Kind of sounds like a silly question. None. So there's a 0 right here. Okay? Got all that? All right. And we defined isotopes earlier. We're going to use all this and isotope symbols to do nuclear equations. You got me? Okay. And isotopes are written the same way. For example, carbon, there is carbon 12. Okay. Carbon has 6 protons, and any atomic particle with 6 protons is a carbon, regardless of the number of neutrons, and therefore regardless of the mass up here. So this is the most common form of carbon. If you look on your periodic table, it's going to tell you the atomic mass of carbon. The average atomic mass is slightly more than 12. And that's because most of the carbons are 12. Okay? But there's also a fairly common form of carbon called carbon 13. Okay? Notice the atomic number doesn't change because to be carbon, it's got to have 6 protons. Anything that doesn't have 6 protons is not carbon. And then we've got the form of carbon that is unstable and therefore radioactive called carbon 14. Alright? And I'll use that as the example to start doing nuclear equations here in just a second. What now? This is the most common. And this is kind of common, but not nearly so common as that. And this is pretty rare, but very important. Okay? Because it's how we date how long ago something organic died, plants or animals. Okay? Which is kind of important in archaeology, anthropology. Okay, and to a lesser degree, geology. Okay, all right.